Hello everyone, this is a very amateur video to help you with the assignment that I've given you today on the properties of rubber. So enjoy the video. I'm sorry about some of the quality not being perfect, but hopefully you'll find it informative and it will help you do the work that you need to do. Thanks. So here we are in my backyard. We have a ladder. We have a sling. Down here we have a bucket. And between the thing we have some hooks which we can test elastic bands in. So you can see we've got a sling which really is just there to stop the bucket crashing to the ground. The bucket which contains a varying amount of sand, so you can change the force on the elastic band. And we have two hooks with the elastic band between them. Here I have a notepad, a pair of kitchen scales, or some kitchen scales, a tape measure, some elastic bands which we're going to test, and a beaker for loading up the bucket. So the first thing I'm going to do is weigh the bucket on its own. That's 862 grams. I'll write that down. So I've tied up the bucket to the ladder, and can you see that little piece of wire there? I've got one there and I've got another one here on the bucket. Don't know if you can see that there. And I'm going to attach a rubber band to those two. So here's the band attached to the two hooks. I've just dropped the sling enough to not to stretch the band at all. I don't want to put any force on it. I just want to see how long it is in its no force state. And I'll write it down. So I'm going to lower the bucket down a little bit so that the elastic band is taking the strain. Just pulling this a little bit to make sure there's nothing in the sling. So that's my extended band with the weight of an empty bucket. Measure it and write it down. So now I'm just going to zero the scales with the beaker. And fill it up with some sand. Pop it on. So that's 325 grams of sand. Pop that into the bucket. Measure it and write it down. So we'll repeat that process quite a few times. I think I look better without my glasses, maybe not. And we'll end up with a very stretched rubber band. So here are my final results. It's quite interesting actually. This particular elastic band starts its life at 80 millimeters and finishes it at 550 millimeters. So there's a factor of about 6 that the band can stretch. So to validate my results, it's quite a good idea to plot a graph here, just to see if any points are crazy or that kind of thing. However, this is not the final result, because what we're looking for is understanding the material properties of rubber, not this particular elastic band. So here's the raw data which I put into an Excel spreadsheet. One thing that's interesting about validation is that when you actually use Excel to add up the numbers, you suddenly find that your mental arithmetic is not as good as you thought it was. So, but that's good. That's called validation. We use the computer to validate our data. So here's the graph. We can see there's a clear trend line. 1 or 2 points perhaps a little bit out, but I'm pretty happy with that. I think that gives us a good basis for future analysis. Here I am on Monday morning. You can see there's continuity errors. This is a new haircut, and I'm also in a new place. But you know, I'm not a professional video producer. I'm just trying to teach you something. So here we go. Strain. What is strain? Well, if I take an elastic band, say it's 10 centimeters long, and I extend it by 1 centimeter, then the strain is the 1 centimeter divided by the original length, which is 0.1 in that case. Now, that's the general way that people will define strain, but technically that is called engineering strain. There is another way of looking at strain, and that is true strain. Let's put this to you. I've got my 10 centimeters and I extend it by 1 centimeter, right? The strain so far is 0.1. We all agree that. But now I have an elastic band that is not 10 centimeters but 11 centimeters long, and I extend it another centimeter. So that extra bit of strain is 1 centimeter, not divided by 10 but divided by 11, which is 0.09. And if I add the two strains together, I get a figure of 0.19, not 0.2. Now, they're both correct, it's just different ways of defining what strain is. So the engineering strain is just the extension divided by the original length. Simple. The true strain is all the little bits of strain added together to create a number. And they're subtly different. When the strains are small, there's very little difference in them at all. But when they're big, it does make a difference. And when we're stretching an elastic band to 5 times its original length, then we probably need to think about true strain as well as engineering strain, particularly when we're dealing with materials. So here's the maths for engineering strain. Epsilon, that's the Greek letter epsilon, and it's what we usually use to represent strain. Epsilon equals, the triangle is delta L. That means the change in the value of L, the length. Yeah. So the change in the length divided by L0, which is the original length. Now let's look at the value for true strain, or the mass for true strain. So epsilon is strain, we still call it epsilon, but this time we've got a little suffix T, which means true. So the true strain is, now this is the Greek symbol sigma. It means the sum of, or lots of things added together. So what's added together? Well, we've got delta L over L, which is, in other words, all the little changes in L divided by the length at that time. Actually, this is not, strictly speaking, what true strain is, because it's still what we call discrete or chunky. Yeah, this sigma sign means we're adding up lots of numbers with reasonable sized intervals for the delta L. Okay, now to get true strain, we need to make that delta L smaller and smaller until it is infinitesimally small. In other words, so small that it's smaller than a coronavirus. Okay, so how do you do that? Well, this is where Isaac Newton comes in, and all his great maths about calculus. All right, so we're going to change that formula to what it would be when delta L becomes infinitesimally infinitesimally small. All right, and here it is. We have the integral of dl over L. dl is the infinitesimally small bit of L, okay? And I've just written it 1 over L dl. So we've got the integral of 1 over L dl. Now we have to have limits with integrals. The original start limit is L0, the original length, and LF is the final length. So that's our formula for true engineering strain. The integral of 1 over L dl between the limits of L0 and LF. So from your maths class or from your A-level maths, you'll remember, of course, that the integral of 1 over L with respect to L is the natural log of L, ln L. So here we are. I've put the value for strain, the true strain, is, and this is the square brackets, which means we need to substitute values. The values are L0, the original length, and LF, the finished length. And the term inside the square brackets is ln, natural log of L. Okay? So what we then do is we say, all right, well, if L is LF, that's the natural log of LF, minus the natural log of L0. And of course with logs, if you've got the log of A minus the log of B, that's the same as the log of A over B. Do you remember that one from your maths? So that is the final formula for true strain, natural log of LF over L0. So let's start by working out the engineering strain in Excel. Here's the length ratio, and here's the value. The formula is the difference between the original length and the current length divided by the original length. Okay, notice in Excel I'm using these dollars. This forces Excel to always look at row 3, so it's always going to get this number here and not some others wherever you paste this formula. On the other hand, the true strain is the natural log, in Excel that's ln, is the formula, of the length ratio. And you can see for big strains like this, they come out with quite different numbers. So after that, it's a copy and paste job in the Excel spreadsheet, and here are the results. So now we're going to talk about stress rather than strain. Stress is not, oh dear, I haven't done my assignments, I'm going to have to work all night to get this done. That is a kind of stress, but it's not what we're talking about here. We're talking about stress in engineering. Okay, now nominally this elastic band has a cross-sectional area. In other words, when I don't stretch it, I can measure that cross-sectional area. When I apply a force, yes, it stretches, that's the strain, but the force divided by that nominal cross-sectional area is called engineering stress. Okay, now the problem is with large extensions that the cross-sectional area actually shrinks. So what are we going to do about that? Well, if we just use the original cross-sectional area, or the reference cross-sectional area, force divided by that, that's called engineering stress. On the other hand, if we were to actually get the cross-sectional area now, which would be smaller, the true stress is actually a little bit higher than the cross-sectional area, than the engineering stress. So, like strain, we've got two different measures. One's called engineering stress, the other is called true stress. Now, the issue there is how do you find out how much the cross-sectional area has shrunk? Well, with metals, it's quite difficult. You have to get into something called Poisson's ratio to understand it. With rubber, we can pretty well approximate that the volume of the band is going to remain constant. So if I've got an engineering strain of 1, in other words, I've doubled the length, then I can assume that I've halved the cross-sectional area. So just like with engineering strain and true strain, we are going to work out both on our Excel spreadsheet. So I went to my dad's old toolkit and found his calipers. Don't know if you can see them. There you are. And I measured the cross-sectional area the section of the band. Okay, and that came to 1.5 millimeters and 2.3 millimeters. Okay, giving an area of 3.45 millimeters squared. Of course, a rubber band has 2 sides to it, so the total cross-sectional area that's being stressed, or which is taking the force, is 6.9 millimeters squared. Okay, so here's my cross-sectional area. Here's the ratio of lengths for the first stretch, and if I multiply the original by that ratio, I get the new area of 3.25 millimeters squared when the rubber band is 172 millimeters long. And I use copy and paste to create a column of areas as the band is stretched. So the next thing we have to worry about is force. Okay, we have everything at the moment in grams force. You need to remember that real force is measured in newtons, and the formula is F equals mg, where m is actually in kilograms. So we basically need a conversion factor of our forces to get into newtons. So here it is. We take the force in grams, we multiply it by 9.81, which is the acceleration due to gravity, and we divide it by 1,000. And of course we copy the row down through the entire column. So we've got force and we've got area. Now if we want engineering stress, we take the force and divide it by the nominal, the original area. If we want true stress, we take the force and we divide it by the actual area. So we do that in Excel and get 2 columns, one for engineering stress and one for true stress. I'm not going to tell you how to plot graphs in Excel. I'm sure you can find lots of good material for that on the internet. What I'm going to show you is the 2 graphs I've plotted. The first one is the engineering strain stress curve, and the second one is the true strain, true stress curve. So what does the engineering stress strain curve tell us? Well, I don't know what you think, but there's a couple of things that are pretty certain here. First of all, we've got about 16.5 newtons per millimeter square before the elastic band breaks. So if you're a designer and you want to design an elastic stretched component and you don't want it to break on its first stretch, you've really got to make sure that the stress, or the nominal stress or engineering stress on that component, is less than 16. Okay, I don't know if you think this is a straight line along here. It might be, it might not be, but the theory is in rubber that it is, and you can see that stress is proportional to strain in that area. So that means that you can have a constant called Young's modulus, which is the gradient of that curve. And just quickly looking at this, we have a stress of about 4 newtons per millimeter squared and a strain of 4. So that would make Young's modulus 1, times 10 to the 6, because we've got millimeters squared up here. All right. The third thing that this can tell you is that this piece of rubber is going to stretch to about 5.8 times its original length before it breaks. Okay, so in very practical terms and in design terms, the engineering stress strain curve is actually pretty useful. So here we have the true strain and true stress curve for rubber. The first thing to note is that the ultimate tensile stress for rubber is actually much higher in true stress terms than it is in engineering stress terms. Practically, this means you could conceivably have a component where the rubber is pre-stretched and you would design it using a stronger material, or it is a stronger material than basic engineering figures would give you. The second thing to notice about this is that the curve is very curved. So rubber really does exhibit a property where it hardens as you stress it. So personally, as an engineer, I think the engineering figures are kind of more useful, but if I was a material scientist, I would definitely be more interested in the true stress and true strain curve. It's kind of more scientific. But what is absolutely important for all of us is that when, particularly for soft materials where the curves are really different, but all of us know what the graph is actually showing us. You need to know the difference between true stress, engineering stress, true strain, engineering strain. And when you see one of these stress strain curves, just think to yourself, well, is this engineering stress? Is this true stress? It's worth just pondering those things. Again, as I say, with metals, it doesn't really matter, but with softer materials, it does. Before we move on, I want to bring in a new material property. It's called toughness, and basically it is the area underneath the engineering stress strain curve. Okay, toughness is kind of a measure of impact resistance. So rubber stretches a lot, it will absorb impact. And if something is very strong as well, it will absorb even more impact. So that area there gives you some measure of how well a substance copes with impacts. If you're into military things, then armor has to be very tough, doesn't it? Okay. Well, I've used the spreadsheet to calculate toughness by looking at energy. Okay, so I've created a new column here, energy, and what I'm doing is I'm saying, right, well, in every segment of the graph, what is the average force? So I average the two forces out in newtons. In this case, I'm adding 8.4 and 0 and then halving it. And then in that segment, what is the length that is travelled in meters? Multiply them two together and I get these energy figures here. If I then add them all up, I get the total energy absorbed by the elastic band in joules, and I can easily calculate the volume by multiplying the cross-sectional area and the original length. I've got the volume, I've got the energy, I can then work out the toughness, which is the energy per unit volume. But toughness comes in SI units, so I have to adjust the units from millimeters to meters. and that requires you to multiply by 10 to the power of 6. So the toughness is 25 times 10 to the 6 newtons per meter squared. Now, before you say it, I am fully aware that this whole experiment is very Heath Robinson. But actually, whenever you are creating an experiment, you have to weigh up the costs in time and effort against the accuracy. Now, if I did have more money and more time, it's actually very useful to do a little bit of self-critique and work out, what do I really think about this experiment? Where are the sources of error? Well, I think the biggest source of error is this thing, measuring the cross-section. These elastic bands are very hard to measure. This is actually a very old measurement. If I had a micrometer, I would do a much better job. And I'd also go around the rubber band and measure it at lots of points and then take the average. Okay, so that's problem number one with this experiment. Problem number two is when I stretched it, can you remember I stretched it on wire? I hooked wire around it. Now what that does is it causes a stress razor around the wire. So in other words, there's actually more stress on the very end of the elastic band than there is in the middle. So what we do in the world of materials engineering when we're doing the job properly is we actually don't use rubber bands as samples. We have to design the samples so that it's a kind of tapered shape, and the stress is concentrated into the long, thin, straight bit of the sample. Another source of error here is the fact that my force measurements were based on my kitchen scales, which are reasonably accurate. But can you remember I actually put in the sand one at a time and I measured the sand as I was putting in it. This is called error compounding. Supposing I had a 10% error with every piece of sand that goes in, that compounds through the force. So really it would have been better if I could measure the weight of a bucket with the sand in one go. Problem with that is I couldn't do that without unloading the elastic band, and I wanted to do the whole test in a continuous stretch. One final little problem is we only did one elastic band, and I would imagine that in the real world every single elastic band, even if they are nominally the same size, actually do not have constant properties. One more, temperature. I didn't measure the temperature when I did the test, and it may well be that the properties of rubber are temperature dependent. Final one, there's loads of them. Final one, rubber actually, we believe, is not a static material. So the properties depend on the speed at which you stretch. Yeah, it's called the strain rate, and I didn't measure that at all. So there you are. There's loads of things wrong. When you do your experiment, I would like you to do the same as I have, analyse what went wrong or what you don't think was right, but also if you can improve on any of the things that I did, please do so. So the point I'm making is any real experiment has flaws, has inaccuracies. It's not our job to brush them under the carpet. It's our job to recognise them and work out how critical they are in terms of what we're trying to do. As a first cut experiment on the properties of rubber, I'm actually quite satisfied with this. But if I was, asked to get it within like 2%, I don't think I would. So before you go, if you look at your assignments, I've actually asked you for kind of extras if you have the inclination to do them. Obviously you get more marks if you do. So number one is have a look at creep. Right now, what I'm going to show you here is I've just measured this elastic band. It's 4.5 centimeters long. Without snapping it now, I'm going to stretch it quite a lot. I can feel it's quite hard there. I'm going to just leave it there for a little while, stretching quite hard. Sorry, you can't see that. Okay. And now I'm going to let go. First thing I notice is that the force letting go is clearly a lot less than the force going in. But if I want to measure that, the question is, has it expanded a bit? And I would say it has. It's probably gone up by about half a centimeter. So that phenomenon is called creep. When you're stretching the elastic band, it is actually deforming permanently. All right. And even though it comes back to close to where it was, it's not exactly the same. So if you would like to study creep, I'm sure you can use your experimental setup to do it, but you'll need to sort of time the stretches a little bit, and you need to look at sort of how much force there is, how much stretch, and leave it there for a little while, drop it back, and see if it's permanently deformed. So that's creep. Now the second one is fatigue. Right? We know that these bands are actually quite strong, yeah. So we pull them. We have to pull them quite hard to break them in one go. But what I'm going to show you now is if I just keep doing that for a lot of time, sooner or later, it's going to break. Okay. Ow! I knew that would happen. Okay. That's called fatigue. So if you cycle loads onto materials like rubber or steel or aluminium, they turn out to be a lot weaker than if you do it on one occasion. All right. So yeah, that's fatigue. Take a look at fatigue and see what you can learn about fatigue on your experiment. Now, one last thing you can look at as well is this thing called hysteresis or hysteresis. I'm not quite sure how to say it, but you can feel it with fingers. You stretch your rubber band. As it goes out, the force is quite high. As you let go, the force is less. All right. So I'm stretching, I'm feeling the force, but as I go back down, the force is less. So that means that the energy that I'm putting into the elastic band when I stretch it is not being fully recovered as I go back. Now, if you can, do an experiment where you stretch an elastic band a bit, measure the forces, but then allow the elastic band to recover as much as it does. Yeah, there's creep, so it doesn't recover perfectly, but recover as much as it does, and try and work out the energy loss in that process. You can also plot the force extension diagram and look at the hysteresis of the whole thing. So, ladies and gentlemen, that's my support video for your assignment. The main thing is I want you to design the experiment yourself and conduct a reasonably successful experiment. When you've done that, make sure you understand the theory and get the ultimate tensile stress, get the Young's modulus, get the get the difference between true strain and engineering strain, true stress and engineering stress. All those things are important. Make sure you do a good job of the basics. If you've got time and you're interested, and I hope you are, then look at these other things like fatigue, like the influence of temperature, like hysteresis, and so on and so forth. Good luck with it all. And I don't know if you know, but Gordon Brown has been listening to the whole thing. He says I need to talk a bit more slowly for him, but then he's not that clever. Anyway, have a good day. Hope you enjoyed the video, and I will no doubt be speaking to you very shortly.